the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 41, where today we are going to be discussing the question, does physics even exist? So, if you guys have seen our episode 2 episodes ago, does math even exist? That's actually a pretty popular one, by the way. So, on that episode, we kind of spoke about the philosophy of mathematics. We kind of spoke about, how math is a conceptual idea at the end of the day and, stuff like that. And today we're kind of going to be doing the same, but for physics. And I think this is going to be really fun.
This is absolutely going to be a riveting episode. Before we do get into the content, though, we do have some quick news. We're going to make this as quick as possible.
Yep.
First up, we started posting clips of the podcast
Biggest
up on
news out
YouTube, on Instagram. Our Instagram is math.physics.podcast. And we have a TikTok, math.physics.podcast on TikTok, where we'll be posting all of our clips. Some of them vary in time length, so we'll be cutting them up for TikTok and all that.
Quick fact, so the clips that we're posting is going to be on YouTube, and the same ones are going to be on our Instagram. Like we have an IGTV now, which I think is pretty cool. And the TikTok ones are obviously not going to be the same because the Instagram ones, can be a lot longer. So like the TikTok ones are going to be a lot shorter. So if you guys want to see quick snippets, even quicker snippets of the clips, then go check out our TikTok. And I think when this episode drops, I think our TikTok should be ready, right? Like
definitely,
we should have videos on there.
Yeah, and so as always, everybody is killing the download and the follower count for our podcast. We will obviously continue to post every single Monday for the time being. Yep. And we have some very interesting interviews coming up, so make sure to stay tuned for that. Once again, this episode is being recorded and posted on YouTube if you want to see our faces talking at the same time. If not, enjoying the audio experience is always great too. That's about it. So yeah. Let's begin. All right. So the philosophy of physics has a lot of ideas that we can talk about, and a lot of ideas that they kind of run parallel to some of the topics we talked about in our math philosophy episode. Oh yeah, wait, one last thing before we do start. Ray and I are going to start talking more as like a conversation between us. True. Instead of doing like a presentation style podcast, because we realize it's just, it's better in general if we just treat this as a conversation between the two of us instead of being like, oh, this, and this, like as if we're talking to you guys instead of talking to each other.
Yeah, so there will still be like obviously a level of, teaching is the wrong word, but education, that's the word. There will still be obviously like a level of educating, others, because at the end of the day, we kind of know what we're talking about, right? So like when we talk to each other about it, it's mainly for you guys. But I think like I was watching a few podcasts and I just noticed that sometimes we're literally having it like it's, one of those online Zoom lectures. Like I'm like, no. So so that's why we're going to try and, get it to more of a, hey, it's Parker. Yo, what you were saying.
Yeah, as soon as we actually start the podcast, we're just going to be treating it as if we're talking to each other.
Exactly. That's the goal.
So anyways,
might take some time to get used to, though. Like we might mess up in like a few episodes, but we're going to get there.
That's true.
Yeah.
Okay, so the first thing I wanted to bring up in this conversation here is that physics is built around being an observer that is alive, whatever that means, right?
Yeah.
There's not really a definition for being alive, because we in biology or whatever, it's like whatever is alive is what evolves over time. Well, not evolves.
I mean, as evolved
like
from something. Is that what you're trying to say?
no, I'm trying to say like because anything can evolve, right? Like a rock can change its shape with
Well,
erosion.
I mean, it doesn't
and all that
evolve
stuff.
in the same way that mammals do, for example. Like,
Yeah,
these are
no,
very
that's what
different evolutions.
Yeah, that's
Very,
what I'm trying
very
to
different.
say.
Yeah, okay.
I'm trying to say like things that it doesn't have to breathe, right? Obviously, because plants and fungi and stuff like that.
They technically breathe.
Okay.
Technically.
Anyways,
I mean, in their own biological way.
Let's just say breathing is like it encompasses everything, like the biological process that makes you alive, right?
So conscious is what you're trying to say, mainly. Well, is that what you're trying to say? Because I mean, that's my interpretation.
Are plants conscious?
Oh, plants are. What you're trying to talk about is like how we define observers. Is that where you're going?
Yeah, basically.
Okay. Plants, I don't think.
Well, here's the thing. Plants, like,
not really.
They react to their environment, right?
Of course. Yeah.
Like anything that is alive.
Yeah.
They react to the environment. So, which means they have senses,
True.
right? They can sense if there's sunlight out, right? Obviously, they can sense when it's daytime or nighttime, like flowers close up and all that stuff. So they have some type of reaction to the universe.
True.
Obviously, this is not like a local thing, right? Well, depends on what scale you're using, but they react to stars because our sun is a star, obviously, which is millions of kilometers away. Mm-hmm. They react to the orbit of the Earth around the sun and all that stuff with like seasons, and obviously the trees lose their leaves and anyways, enough talk about plants. What I'm trying to say,
why are we so deep into plants right now?
What I'm trying to say is that anything that is considered alive is an observer, right? You might disagree, plants aren't observers. Well, they observe somewhat what's going on
in a sense. Yeah.
And so what I'm saying is that physics as we know it depends purely on who is observing.
Observation, true.
Because, the fact that we have eyes will obviously affect how we measure things. AKA, you wouldn't be able to measure the brightness of stars if you didn't have eyes. Or maybe, I don't know, maybe there's some type of weird tool that you can conjure up, but anyways.
Okay.
What I'm trying to say is that being an observer in our universe, in our space-time universe, is what shapes our study of physics. Mm-hmm. And physics is, an observational science. You look at things and you try to describe them, right? If
you think about it, though, all sciences to a certain extent are observational, like chemistry. You're observing, when you mix two chemicals together or something, what happens. Biology, under microscopes, you're looking at certain cells and certain reactions. So at the end of the day, I think all sciences, even though we are focusing on the physics of it right now, like all sciences are in some way highly observational. And without that observer there, like none of them can really truly be ever written. Right? Because the entire reason for how they were written was with observers who observed certain effects, right? And those effects is what we now know as physics and chemistry and biology.
Yeah, and in a sense, there is no distinction between physics, chemistry, and biology, right? Because at some point, what you study in physics borders what you study in chemistry. And what you study in chemistry borders what you study in biology. So it's all kind of this continuous spectrum of...
Because physics is kind of like a smaller version of chem, and chem is kind of like smaller as in more precise, more... Like, we're kind of zooming in, right? Like, you see the human body, it's biology. You go to your organs, it's biology. You go deeper into, how they're... like energy transportation, that's chemistry, like bordering chemistry, biology. You go even deeper into quantum entanglement or quantum tunneling in your body, which definitely occurs. That's where you borderline physics, right?
The reason why I prefer physics
Okay,
is
let's hear it.
because yeah, it's kind of like a smaller version of chemistry / biology, but at the same time, it's everything. Like in physics, you study every scale. You study the absolutely microscopic subatomic scale, and you also study the human scale, right? Like the motion of objects and the gravitational pull and forces and all that stuff. And then also up to the cosmological scale, where you study the most massive and the largest distance-wise objects that exist in the universe. And so it's like you get a piece of every single kind of
It's
scale.
kind of, yeah. I think that's the biggest advantage, because like in physics you have the quantum realm and you have like, you know, the cosmological realm, and those are complete polar opposites, yet you know still exist in the same field, which I think is a pretty interesting, you know, phenomenon of it. So yeah, so just talking about, you know, how physics has the ability of describing our universe, I think a little differently, or at least this is my opinion. So in the Does Math Even Exist video, right, we were saying that math at the end of the day is a very conceptual topic. It's very abstract, right? Like it doesn't really represent any physical thing. However, physics, on the other hand, right, like that directly describes certain physical, you know, phenomenon. For example, F equals ma, right? The most of a very easy example, or your force of gravity equation, you know, your mass over r squared. So all what that is explaining is what we physically observe, right? Like if you push something with a certain force, it accelerates. You can observe that using these physical equations. So that's why I think physics, a little differently from math, is not as conceptual, but describes the universe in a different way and a realistic way. What do you think?
As I said earlier,
Yeah.
like in our previous episodes, like physics is using math to its advantage, obviously, because
True,
it's
of
much
course.
easier to write things down mathematically versus in English trying to describe relationships. You know, describing a linear relationship is a lot easier when you just use symbols instead of trying to explain. The thing about physics itself is that it's built around the ability to write things down. The fact that I can look out into space, see something going on, and then I write it down. Realistically, what's you know, it doesn't matter that I can actually physically write down the relationship. It's the idea that I can take an observation and form that relationship in essence, right? So that idea, that relationship exists in my head. And so my take on it is that physics is not real. Answering the question of the episode, right?
Yeah.
I don't think physics is real. I think physics is just it's a body of knowledge, right? It's just this well, it's an infinite. It's like the real number line, right? There is no bound to it, but we only hold as much as we know, right?
Okay.
When we keep expanding our knowledge, but there is, or in my opinion, there is no end in sight, right? There is no real, well, that is a whole topic on its own that we did talk about last time.
But see, if you think about it, like physics, like even though is, you know, world of knowledge, I don't think you can say, like, for example, then you can use that same argument for any of the sciences, like even chemistry or biology. Like they don't necessarily have to, you know, if we're just talking about chemistry, it represents,
that's true.
you know, different realms of knowledge, right? And they can be applied in different ways. Obviously, we're not even close to knowing how much chemistry there is in the world, right? We're not even close. Same way with physics. So at the end of the day, if you just talk about them like just as a subject, I think, yes, I can definitely see your point. Like none of them truly exist. but it's when we, apply it to real life phenomenon, to real life observations, as you said, like we observe something and write it down. Like that equation, what we call physics, represents that real life phenomenon. So would you not deem it to be real of some way?
Here's why I
some
don't
sort.
think so.
Okay.
Because let's say we use Newton's equation to find a force acting on an object.
Okay.
And we find that number, okay? But do you think that number, like the result that you find, it represents a real thing? Fair enough.
Yeah.
But in reality, it is just an approximation but well, hear me out,
Yeah, I'm listening.
It's just an approximation, a fairly good one. Right? I'm not going to say it's a great approximation because there are many situations where it does break down. But, let's say we're under mild conditions and we find a result for a force that's acting on an object. That result depends on our observation, right? It depends on what we observe the acceleration to be, what we observe the mass of the object to be. But if you do believe in like a deterministic universe, then you do believe that there is, in essence, right, in its purest form, there is an exact number that represents the force being acted upon the object.
That is true.
That right?
That
you think
true.
that like it's embedded in the code of our universe somewhere.
Of course.
That there's a perfect number that exactly
exists.
describes the force being applied.
Okay.
The reason why I don't think that physics is real is because we will never be able to get to that number.
True. That is a fact.
Using physics.
That is
physics is just, I think it's like there's a muddy lake, let's say, and you're trying to find the gold, the gem that is at the bottom of the lake, right?
Okay.
Physics is kind of like these binoculars, right? You can kind of zoom in to the mud and the cloud of dirt, and you can see like a sparkle, but you'll never be able to just see exactly where that gem is.
Yeah. True.
To actually figure that out, you need to plunge into the lake and actually grab it, which is only the hand of God can perform that action in terms of physics.
I think this is that is actually a fantastic point that you brought up, because I was actually because when you were talking about that, the first thing I thought of was uncertainty, right? And in almost any kind of lab class that you do in university, or any physics lab class, or any lab class for that matter, you will definitely encounter uncertainty propagation. Or what that means is calculating the error in your observations or in your measurements. So you will find out that, believe me when I say this, obviously, like, I just finished the semester, so I just finished my lab class, and there were so many reports where I forgot to put the uncertainty in like these small variables that I thought wouldn't matter. But basically the moral of, getting all those marks deducted from my reports was every value, every observation has some level of uncertainty. So what Parker said there was actually a very good point brought up, because at the end of the day, every force or any equation that we calculate will have some uncertainty relating to it. So as you said, we won't get that exact force. We never will, because that force will have some uncertainty relating to it. So we're never going to get the exact number. And that's just unfortunately a consequence of physics or I think just measurements. Right? Like everything has its own embedded error, right?
That's
and
right.
Because we can never get the perfect precision on almost anything. Like even a ruler, if you're measuring 10 centimeters, it's never exactly 10 centimeters. There's definitely an error, So there's always that small thing that people miss, don't really talk about. No one really talks about error propagation, but it's a very, very important discussion. Especially
and you can also check out our episode on error analysis, which we
Yeah.
did a
That was so
couple of
long
months
ago.
ago. Yeah,
That was
a while
so
ago.
long ago.
But it was a fun one.
Wait, I think that was one of our single-digit episodes, eh? Like one of like.
No, I think it was in the tens, the teens.
Was it? I swear I thought it was
I
8
don't
or
know.
something.
Anyways,
Not that that matters. But
so
okay, yeah. Continue.
yeah, okay. So I was gonna say that my favorite expression on this podcast back in the day.
Okay.
Right? Newton said, well, he didn't say explicitly, but his take on physics was that physics is all about finding forces, right? It's finding the forces that act on objects, and those forces will give us the motion of objects through time. So, you determine the forces, those will give you the accelerations, the velocities,
The momentums, the positions,
over
the
time,
whole thing.
and you will get a description of what's going on physically. But after Einstein showed up and he found that space and time were interlaced, right? They're dynamic. One is not separate from the other, but instead it's this four-dimensional grid that you can, place events on,
Manifold.
right? Depending on the space-time coordinates, which sounds really fancy, but if you're not like a physics person and you hear, oh, space-time coordinates, it's not that complicated. It's just, you have your spatial coordinates, which is, let's say, okay, 1 meter over here, 1 meter over here, whatever. You have your space coordinate and your time coordinate. Time
True.
equals 1 hour, right? There's your space-time coordinate.
very,
This
very
position
basic example,
at this
but
time. And then to see how your coordinates evolve, you just have to see where am I versus where I started, and also, how much time has passed.
Time elapsed, exactly.
Which is like the reason why it's such a groundbreaking idea that space and time are together as one, is because as you move in space, you change the experience of time. I guess that's not very
Maybe you would want to explain
accurate.
that a bit.
Yeah.
What do you mean
Because-
your experience of time? Are you just trying to say that your time changes?
Well,
Or-
I mean,
what do you mean
the fundamental
experience?
idea is that the speed of light is constant for all observers.
True.
And so to keep that fact, and you start to study velocities or relative velocities and accelerations and all that, you see that for that fact to hold, you need your time to slow down, or your
As your speed increases.
your distance to stretch or whatever. And so you see that the fact that you are moving at a certain speed relative to something else will affect your spatial description.
That's what you mean. Okay.
Yeah. So basically, I'm just saying one affects the other, essentially.
Basically, space affects time and the other way around as well.
Yeah.
Like time dilation is a fantastic example. That's
Exactly.
basically, I think, what you were trying to say, right?
Mhm.
Like time dilation perfectly shows how, how your velocity or the speed at which you're moving through this space changes how time works for you, right? Like that can be thought of as an idea, right?
Once
So-
again,
yeah.
we did talk about this in our special relativity episode.
Yeah.
We are coming out with a part 2 to that, which
Part
is
3, isn't it?
part 2. No, we did a part 2 of quantum mechanics, but not a
Oh
part 2
yeah,
of
sorry.
special
I'm
relativity.
thinking. Yeah, true.
That
Yeah.
is coming soon as well.
Mhm.
But what I was trying to say with this entire thing, by the way,
Okay.
is that physics became less about the motion of objects through time and became more about finding the deterministic laws of nature, right? It's, we kind of zoomed out a bit because, of course, there are laws that determine the motion of objects as time passes. But once you realize that everything is connected together, physics becomes more about what can we know exactly. And Einstein believed in a deterministic model of the universe, which just means that everything, if I want to be broad here, everything has like a foreshore value, as I said earlier, right, that gem that you're looking for exists somewhere, and it is possible to find it. Einstein believed in that, and which is why he opposed quantum mechanics, which we'll get to.
We'll get to for sure.
A couple of minutes.
Yeah.
What I was trying to say, Einstein determinism. Yeah,
that's essentially right?
That's what I was trying to say. Right?
Yeah.
He realized that finding the deterministic laws of nature, that those laws that can get you to the precise exact values that are embedded in our universe, is what physics is all about.
True.
Yeah.
That is true. So we were also talking just recently about time, right? And I really want to add something on there, because I think when we're talking about, sorry?
Gotta take off my hoodie.
Oh, okay. We're having a little pause here. Okay. Quick dress rehearsal.
I was warm.
Oh, okay. You're just warm. Okay. I'm just like, okay, that was interesting. Okay, so as we were saying,
dress rehearsal.
So as we were saying, time, right? Time is a very interesting topic, because as we're talking about the philosophy of physics, right, a very important subtopic is the philosophy of time. Because I think the most interesting ideas, especially like, those late night thoughts when you're just like, what is time? Like, what are we really moving through? When we say 1 second, like, what does that even mean? And
why it's something funny?
Okay.
This is not this is just a thought I had, okay? But imagine this, right? Everybody has memories of events that happened in the past.
That's true.
Okay, but imagine this, okay? You form your memories by living in the present. True. And then the images of the events that occur stay in your head. But what if you are already dead?
Oh,
right?
Damn.
No, but think about this, okay? You are already dead. The illusion of the present is you, like, thinking back on your memories of the past. So right now, we're recording a podcast. I'm sitting at my desk and I'm talking to a microphone. But right now, the present I'm living,
this is just memories.
This is a memory being formed in my mind.
It's way too accurate to be a memory, man.
That I'm remembering, right?
Way too accurate to be a memory.
But how do you know that?
That's true. I guess that's true.
You say it's way too accurate to be a memory.
So wait. So I am remembering.
Yeah, right now
sometimes
you're remembering.
I can remember a memory, is what you're trying to say? Like, I'm remembering something that I remembered?
Because like 90% of your day you don't remember. Right?
I mean,
like if I ask you 3 weeks ago at 1 p.m. what were you doing? Like, you don't know exactly what you were doing,
food,
right?
Man. I'm kidding.
But the events that you remember, when you remember, oh yeah, this happened, what you're actually like that memory is you having like a flashback to the present in the past. Does that make sense?
Okay, so that's definitely a thought. I don't know where that came in from when I was talking about time, but that's definitely a good thought.
Oh, this is just to say that the passing of time is just an illusion altogether. Like, there is no present, past, future, because you're already dead, so it's all past. Like everything is in the past.
You're already dead. What a fantastic way to describe it.
Like, there's no distinction between now, earlier, and later, because everything is just before.
That's phenomenal. Okay, so that's an interesting idea. Definitely think about it. Put in the comments what you guys think about that thought. If you guys agree with Parker, or just think he's absolutely insane. So yeah. Okay, continuing on to time, right? Like, the first question that comes to mind, especially when we're talking about, the universe or like physics in general, is, well, where did physics or everything really start from, right? Where did time start? Well, the most obvious answer to us, at least, would be the Big Bang, right? Assuming the Big Bang theory is correct. time literally started, like 0.0 seconds was when the Big Bang, occurred. Or at least that's how we think about it. So all of time, started at that point and is now advancing forward. Well, you want to say something?
Yeah.
Okay.
You say time started at 0.0 seconds.
Okay. A lot more point zeros. Yes, of course.
No, wait, no, that doesn't change.
No, because, technically 0 without any decimal places would be the most accurate.
That's not what I'm trying to argue.
Oh, that's not what you were trying to say. Okay.
What I'm trying to argue is that did that point ever happen? Like, did t equals 0 ever happen?
Well, that's the thing, right? Like,
or
if we're talking about things happening require a time interval for them to happen in, right? Like all these eras in the Big Bang that we were talking about on the Big Bang episode all happened in a time interval. But t equals 0 is not really an interval. It's a point. No, so how can that happen?
But my idea, and this is just like a spontaneous idea here.
Okay, let's hear it.
Like, imagine time is like 1 over x, right? The graph.
Okay.
Right? So it goes to infinity at 0, right? So like something like that. It's just like a mental picture. So you can pick any interval of time going all the way up to 0, but not including 0. But saying that something started at 0 is just not defined. Like, you can't have something start at 0.
Okay, so time is technically, that's true. Time is not defined at 0 because nothing. Well, yeah. I mean, I guess you can think about it like that because time.
As far as we know, nothing was real. Like, we were purely on the imaginary plane, right?
Yeah, I mean, like, we had no idea what was happening. We weren't even here yet.
And so if you think about your experience as an alive observer, as like a series of images, right? Just like flowing through time, just like what your eyes see.
Okay,
it's just like a series of like frames, right, passing through time. And this is actually. There are a lot of implications to this, but if I want to be really hand wavy here, if you imagine those frames, right, you can't place one of those frames at t equals 0 because what would be there, right? It would just be.
But again, t equals 0, in my opinion, I think is just like it's a theoretical idea. It's where we describe the universe starting. Because if we were to say, hey, tell me a starting point for the universe. Well, we can't give you one. Well, in position coordinates, it would literally be the origin because there is no universe at this point. There's nothing created. There will only be an infinitesimal, 0-dimensional object, a point, right? Because a point is a 0-dimensional object.
I don't know if I agree with that. When you say, okay, the singularity of the universe is at the origin.
No, because no. I mean, I'm not trying to say center of anything. All I'm trying to say is, if you think about it, no space has been created at the Big Bang. Like, before the Big Bang is just like wrong terminology, but like I think you know what I mean. Like before the expansion occurring, right? Like that point occurred at t equals 0 is all I'm trying to say. And then from there, at that point, because nothing had been created, it's simply a point. A point is a 0-dimensional object. Nothing had been created, so there's no space. So technically, if we're trying to put a coordinate system on this universe, well, there's going to be no numbers. It's just going to be 0, 0, 0, right? So it's going to be the origin.
But
because it's a point, right? That's what I'm trying to say. That's what I'm trying to say. So it's that point, and then from there, you can think about it in the same way with time, right? It's not that it actually physically exists or we can find something about it. It's just that that's how we represent the starting of the universe, right? As t equals 0. Like, it's all just a representation by us. And I think that's basically it, right? But yeah, so continuing on to time, what I really wanted to talk about is how we came up with time, right? Now, I've actually done quite a lot of reading on time, And
Have
for
you
some
now?
reason, I can't find an exact answer for why it is the way it is. Let me explain what it is first. So originally, before we have all these atomic clocks and, very precise measurements of time, what people used to do, and this is purely off the internet, so I can't really go deep into it, it's basically they used to have this thing called the ephemeris, which listed all the orbital positions of different planets in the sky. And when they compared the current position and how these objects in the sky were moving relative to each other, and when they compared that to this thing called the ephemeris, they literally came up. This is the part I couldn't find. I really couldn't find where they came up with this number. I swear, I tried. I really couldn't. But, so this number, they got to this pretty preposterous number. I don't even know how. And it's 31,556,925.974 of these time intervals that they made up makes up 1 year. And that's basically how it was defined. And again, I tried looking, man, guys. I tried looking for why it was defined like this, because I want to know. To be honest, I really do. And we can have a quick discussion on why we think it was like this. But basically, the way they defined it, this was the length of the year 1900, only that year. Why? Because technically, exactly every year, the length changes just about a bit. So obviously, with technology advancements and stuff like that, they couldn't keep doing this because every single year, the positions of the planets change. It's not absolute. So this ephemeris that they had, this list of orbital positions, didn't really work because every year it would change a little bit, here and there because of precession. So with increase in technology, they found a perfect atom to do their job for them. They found cesium-133. And the reason they found this atom is because once this atom is hit by laser, right, the outermost layer of the atom, it transitions between these two levels. It oscillates back and forth between these two levels. And that's what we call a hyperfine transition, right? And when researchers calculated how many of these oscillations are required to represent one ephemeris time interval, right? Like one ephemeris time interval, they found this number, right? I'm just going to repeat this number. Probably won't mean much, but 9,192,631,770 oscillations of the hyperfine transition. That makes up 1 second. And because that obviously doesn't change, right? Because the outermost layers of the same isotope will obviously not change in their oscillation period. So when it's hit obviously with a certain laser, it oscillates at this. And these number of oscillations make up what we call today as 1 second.
Okay, but at the end of the day, even though we have this atomic clock,
yes,
that defines 1 second. 1 second doesn't mean anything.
At the end of the day, it's what we defined. It's all based around, I think the entire idea is based around the Earth, around the sun. Because the second is kind of, if you think about it, dependent on the year, right? Like the second, like the way we defined it, is perfectly dependent on how long 1 year is. And then when we take that knowledge, we can think about, it kind of makes sense because 1 year, should have the exact same amount of time intervals every year. Like that shouldn't change. Mm-hmm. Even though the planets and everything is changing, like orbital positions, even though all of that is changing, the definition of a second shouldn't change. So that's when they changed it to the cesium idea with this atomic clock. And they made it a lot more precise such that obviously it never changes. But as you very well said, it's not really it's not a universal constant, the second. It's not a universal constant. It's simply how we have defined this time interval. Like another alien civilization, if they're measuring, I don't know, one second instead of second. I don't know. Maybe it's in their language, 1 second. Okay. Right? So the second might not be the same number of oscillations. Maybe instead of 9.1 billion, it's, I don't know, 8 billion. I don't know, because their planet what am I trying to say? Because their planet revolves at a certain different distance than Earth. So it all depends on how we define it. And I think especially with, time, it's all that we've defined time. It's not that it's really a thing. We've defined the interval of time. So it's not a universal constant. And I think that's a pretty important, idea.
So to get a little bit more philosophical here, back on the philosophical
that wasn't
train.
very philosophical. That was more, I get it. But it was still an idea. Cool idea.
Yeah, how you would define 1 second, okay, could have been very different based on literally everything. So these ephemeris seconds are it's just like an estimation, basically. Okay, we recorded a year and then we divide it up into 31 million time intervals.
Exactly.
That's 1 second. And then later we defined the hyperfine transitions, right? But that's also based off of the ephemeris second.
Exactly.
So if we would have said that a second is a month long, it wouldn't be very useful, but we would just have, instead of calling what we have as a second now a second, we'd call it something else, but it would still represent the same thing. But it might be even a different time interval. It might be the world would still be the same if 1 second were 3 seconds.
Of course. The world would be the exact same. Our calculations are based around the fact that 1 second equals that. Every single thing, I think, in physics, all the equations and everything basically depend on how 1 second is defined, right? At the end of the day, because if a second is different, the speed of light is different. If a second is different, right, the speed of light would be different.
Yeah.
And then that would cause all kinds of problems in a lot of equations that depend on the speed of light, right? So it's kind of like a cause and effect where we've just said that this is it and we're just sticking with it. It's not that it's right or wrong. It's just something that we've come up with, and everything is based off of this.
And that is a consequence of, our freedom of choice.
Yeah.
Which is, it's a topic in philosophy, but not necessarily related to physics. But, we were free to choose what 1 second was or what 1 meter is. But I think that's a little bit more scientific. I think that's the meter is defined from the second, right? Because it's like a distance that that light travels in one fraction of a second.
So
Anyways.
Whatever the speed of light is, that 2 million or that 299 million meters per second or whatever. So it's 1 divided by that number, the distance that light travels in that much time.
Yeah.
So it's kind of it's dependent on that.
But at the same time, the speed of light is defined off of...
it's so weird. It's so weird. So weird.
But how that contrasts to mathematics, where we have constants like pi, e, and phi that come up a lot, those would only change based on the what's it called, the base that you're using. What is that called? Base 10, decimal, binary, all that stuff.
Oh, dodecimal and all. Just wait.
The only way those constants would change is if you're using a different base as a number, as your number system.
Yeah, wait. Yeah, a number. Yeah, I remember. I know what you're talking about. The Dewey Decimal System is base 12, but is that all it's called? Just base 12? Maybe, yeah. Because what we work in right now is base 10, right? Because 10, 20, 30, 40. But base 12 is simply where 12 can be, represented in the same way, and actually can be very helpful in some cases. But yeah, not talking about that. Continuing on, we said we would talk about this, but we didn't. Quantum mechanics. And I think this is kind of the one that breaks, all of what we were saying before about determinism, or at least the idea that we have right now. The interpretation of quantum mechanics that we deal with today is called the Copenhagen interpretation, right? And that entire idea is that quantum mechanics is probabilistic. It's all about, an electron is not here It's not here either. It's probably 30% here, 70% here, but it's
Well,
not.
actually,
Oh,
that's not.
no. I'm just trying to give a
accurate.
very easy example.
I know, but technically there is a 0% chance that you find an electron here.
Yeah. No. Of course.
The probability comes when you look at a certain interval of space. You
Of course.
there is a 25% chance that it is between here and here, because maybe if you do study quantum mechanics, you'll see that when you're looking at the probability density of, let's say, the position, the one-dimensional position of an electron, it's not, or sorry, what I'm trying to say is that it is an integral. And when you integrate from one point to the same point, it's zero.
It's zero,
so
exactly.
If you want to get an
really
actual result, you need to integrate from, let's say, 0 to 1, and then you'll get a probability.
Yeah. So that's obviously a much better description than here or there. I mean, I was just trying to give like the very basic just idea behind the probabilistic nature and how, quantum mechanics says this very interesting thing, which obviously Einstein hated and all these popular physicists hated, because they're like, this doesn't make any sense, right? Because it breaks our basic idea of determinism, right? That everything should have an exact value. Like, as Parker said previously, right? As you said, if I'm pushing an object and I have a certain force, even though we can't find that exact force that exists, that exact force exists. But when we talk about quantum mechanics, like, that exact number does not exist. That's the whole thing, right?
Exactly.
Like, we're not sure where, like, if we were to ask you, where is this electron in, this region of space? Well, we can't give you an exact answer. We can give you a percentage in certain regions, but we can't give you an exact answer.
Actually.
And then we can also talk about the uncertainty principle. I was kind of getting,
Yeah, but no, what I wanted to say was that we can give you an answer, but that would essentially destroy the
momentum.
state.
Exactly.
So if you have an electron orbiting an atom, let's say, and then you wanted to know the exact position, you can in fact measure the exact position. But by measuring the exact position, you're basically destroying everything else about that system, and it would become essentially useless. Like, let's say you want to measure the polarization of a photon. Once you measure that polarization, you can't go back in time and have this probabilistic, 30% horizontally polarized, 70% vertical. No, like, once you measure it, boom, you've destroyed any uncertainty about it.
So in quantum mechanics, so the reason that the reason that works is because in quantum mechanics there are these things called compatible observables, right? Basically, that complicated phrase means, can I measure these two things without changing the state of the particle? That's the whole thing. So the most, the most fundamental incompatible observables in quantum mechanics are position and momentum. So when we say position and momentum are incompatible observables, what that basically means is you can't measure position and momentum and have definite answers for both of them. Like, that is just physically, by the laws of the universe, impossible, because they're simply incompatible, and that's just how we define them, right? But the thing is, the way we define momentum and position, right? Like, momentum kind of depends on the speed, and position as well, where it's located. That also brings rise to the common, the quantum model of the atom, which some people might have seen, like the clouds around the nucleus instead of like the straight like lines. So like in the Bohr-Rutherford diagram, right, we have solid circles around the nucleus. But in reality, in a quantum model of the atom, we don't have these solid circles. We have these clouds because we're uncertain about where exactly the electron is. So we can still know somewhat of position. We can still know somewhat of momentum. Both of them will have some uncertainty. But there is no way in physical reality that both of these uncertainties can be zero. And that's just the Heisenberg uncertainty principle.
And the reason why this broke our understanding of reality itself is because suddenly we knew nothing.
Yeah.
Right? we went from thinking that, oh, physics is a complete description. And this was even before Einstein, right? People thought that Newtonian physics was the ultimate answer to reality. It's like, okay, there's nothing left to understand about the universe. And then Einstein came, and then quantum mechanics came. And the reason why quantum mechanics is so like insane and so non-intuitive is because of that probability. Essentially, you're leaving the state of the universe up to chance, right? You can't tell exactly what's going on. You can just say there's a chance that this is what's going to happen, and there's a chance that that's going to happen. And that is fundamentally philosophical, because if you can know something and nothing at the same time, and you can never know everything, then what are we actually doing here?
That's true. So, quick aside, sorry, I just noticed that my battery's at 8% and my charger is on my bed, not plugged in. So, just quick black screen here. Okay, so right after that black screen, I'm going to put a black screen, and then I'm going to...
But you don't have to put a black screen. You can just
No, black screen as in like a cut scene.
Yeah.
Like a cut scene is what I meant. Sorry, man. Sorry. I just fully forgot to put this guy in. Okay, so 3, 2, 1. Okay, so after plugging my laptop in, we're all good to go. Also, quick note, we are bordering like around 50 minutes. I think there's one thing that I really wanted to talk about in this podcast, which is time travel. Because I think that even though that's not philosophical, like it is still it's basically a concept, right? And it's a concept that we can definitely get into the philosophy of. Unfortunately, we're again at 50 minutes. So, because that's a pretty long topic. So this will have to wait
to the next philosophy of science that does blank even exist series that we have here on this wonderful podcast.
Let us know if you guys like this series. I mean, I think it's pretty cool that the does blank even exist, and let us know any topics that you guys want us to cover. So if it's like, I don't know, whatever you want, you're free to think. Free to think.
Okay.
Free to think about anything.
So if you enjoyed this episode, make sure to go subscribe on YouTube, because this is being recorded and posted on YouTube. Make sure to follow on Spotify, follow on Apple Podcasts, Amazon, other places as well.
Any platform that you are on,
that's right.
Go follow us there.
You can also find us on Instagram at math.physics.podcast, or at the same handle on TikTok, starting very soon. You can also go and watch our clips out now on YouTube and on Instagram.
Yep.
All right. By now, you already know. A lot of people are actually.
Sorry, quick note. A lot of people are liking our Instagram clips, and I like that. A lot of people are viewing it, which is kind of nice. It's always nice to see that. So so continue viewing it, and obviously, if you can, also view it on YouTube, because those are pretty cool. Because I mean, like, we put a lot of effort into like the Zoom episode, and when we put it on YouTube, we're like, oh, let's see this, and then no one watches the YouTube one. Everyone's on Spotify.
I mean, we have a like, for the amount of effort that we put in, we have like a respectable
we're recording
amount of...
it right here. Okay, so I totally understood why people didn't want to watch the what do you call it? Like the pictured podcast. That makes sense. But obviously we just started the recorded ones. So, let's give people time. Let's give people time to think about it.
And, hopefully we're going to get more subscribers on YouTube because of the clips. I don't know why we haven't started doing this earlier, but
we really never thought of this.
We're going to be putting out a lot more content on YouTube now. So
for sure.
We're going to be on our Joe Rogan grind now. So make sure to leave us a comment. We'll definitely answer. Send us an email at math.physics.podcast@gmail.com. And we will catch you in the next episode coming out next Monday. So this has been episode number 41 of the Math and Physics Podcast. Yep. I'm your host, Parker.
And I'm Ray. And we will see you soon.
See ya.